Hello and welcome to today's webinar. My name is Caitlin Karolenko and I'm Scientific Program Manager for the Institute of Advancement of Food and Nutrition Sciences. Before I introduce today's speaker, I'd like to tell you a little bit more about IAFNS. IAFNS, for those who are not familiar, is a nonprofit organization focused on advancing food and nutrition science for public benefit. This is done by bringing together scientists from government, industry, and academia to identify areas of common interest and develop projects to advance science in those areas. As an organization, IAFNS funds and convenes experts to deliver a variety of products to include competitively funded research, workshops, dialogues, and peer-reviewed publications. This particular webinar is supported by the IAFNS Assembly on Scientific Integrity. With representation from all three sectors of our membership, the Assembly is active in ensuring IAFNS achieves and promotes the highest standards of scientific integrity. As we're going through the webinar today, if you have any questions, please go ahead and click the question mark button at the top of your GoToWebinar panel and enter your questions in the box below. The questions are only visible to IAFNS staff, and we will have time to address those questions at the end of the webinar. So today I'd like to go ahead and introduce our speaker for today's webinar. Dr. Andrew Brown is the Associate Professor in the Department of Biostatistics at the University of Arkansas for Medical Sciences and Biostatistics Core Director for the Center for Childhood Obesity Prevention with Arkansas Children's Research Institute. There we go. He conducts research on research through qualitative and quantitative research summaries, characterizing reporting practices that perpetrate scientific misinformation and evaluating methodological and statistical choices that may lead to misinterpreted research. A full bio for Andrew can be found in the handout section. And with that, we can go ahead and welcome Andrew. There we go. I see your slide set.
Excellent.
There we go. And the floor is yours, Andrew.
Well, thank you very much. We had a wonderful tech check just before all this started, and 2 minutes ago, my computer decided to update software for my camera. So just made it on time. Never a dull moment. But that makes it a little bit more realistic and engaging, I hope. So I hope you'll feel inclined to share questions as you go along, and we'll hopefully be able to answer some at the end. So the title of this is toward more rigorous and informative nutritional epidemiology. And one of the questions I got as I was preparing this is this just going to be denigrating observational research? And the answer is no. The title indicates that in at least two ways. And the first is I have nutritional epidemiology colleagues that like to remind people that epidemiologists do trials as well. So they do use the full range of methods available to them. But the other is that, this is a goal towards making nutritional epidemiology more rigorous and more informative. And if I thought that, we should just integrate observational evidence, and there would be nowhere to go. So I have my disclosures here. I'll be able to share slides if you would like, and this can be made available. The biggest things I want to point out here are that the views are my own and don't necessarily represent the views of anybody else. I always like to say, if you like what I have to say, then please share the credit with them. If you don't like what I have to say, then just blame me. But I also have had a bunch of great colleagues and collaborators who have made this work possible, and I try to recognize them throughout. So the extremes that kind of struck us over the years are that basically nutrition epidemiology should be stopped, and the other is that it is fine. And so one example of the extremes is this quotation from Johnny Anides, and it's that nutrition epidemiology is a field that's grown old and died. At some point, we need to bury the corpse and move on to a more open, transparent sharing and controlled experimental way. Clearly one extreme. And then another extreme is nutrition epidemiology has recently been criticized on several fronts. These criticisms, to a large degree, stem from a misunderstanding of the methodologic issues. And misunderstanding these issues can lead to the non-constructive and sometimes naive criticisms we see today. So the other side is, well, people just don't get nutrition epidemiology and everything is all right. So both of these quotations are getting a little bit dated, but they're just two of the most striking examples of everything's a mess and everything is fine. And you can see that in a lot of the conversations that we have often about nutritional evidence. I'm sure each of you have had some conversations about either trials or ordinary association tests. So these conversations that we had resulted in a meeting that we put together with the same title here, Toward More Rigorous and Informative Nutritional Epidemiology, that we put into this proceedings document. And the subtitle there is The Rational Space Between Dismissal and Defense of the Status Quo. And so you can see, we had a great group of investigators, and for anybody in this field, you wouldn't probably be surprised to see David Allison on this list. And so this is while I was at Indiana University, and we had a great time working together on this and pulling some people together. But these are topics that we talk about quite a bit. So we have two short courses. One is Strengthening Causal Inference in Behavioral Obesity Research, and the other is Mathematical Sciences in Obesity Research, where one of the things that we're really interested in is strengthening the research that we do. And the four kind of domains that we touched on in this event that we held was stronger designs, and you can see a few examples there, and we'll talk about some of these. Another domain is stronger measurement, and that is probably one that you hear more critiques about, particularly the self-reported food intake. Stronger analyses, and we'll touch on some of these, and then stronger execution and reporting. So we're going to touch a little bit on each of these today. The report we put together touches on them a little bit further, but every single bullet point you see on this slide is basically a field unto itself, where there are multiple investigators working on just these types of topics, either developing the methods or implementing them. And it's really exciting. It's exciting to see all of that go forward. So we're moving increasingly towards getting more informative information so we can learn more about the effects of nutrition on health. Some of the examples I'm going to give may seem like they're skewering some research and some topics, and in some cases that's true. I try to point those things respectfully, but I want to emphasize the building and the moving forward. If I do show an example of something that I find to be a problem, I try to leave the names off, because it's not an issue of critiquing researchers, it's an issue of building the science. And it reminds me of a quotation by Stephen Jay Gould, which is, "Science moves forward as much by critiquing the conclusions of others as by making novel discoveries." So I want any critiques that I present to be considered constructive, and again, not denigrating. And I know that it's a hard line to see sometimes, but please do take any critiques I mention in a constructive way. So the first idea with stronger designs that we often throw out is this idea of a hierarchy of evidence. And I put a question mark there because this is a deceptively simple concept. And this is just one version that you might see. I have a small collection of them that I've been putting into a file every time I see somebody come up with a new hierarchy of evidence, or a different order, or a slightly different conceptualization of it. But traditionally, this is what we see, is that research synthesis is at the top, a randomized controlled trial is below that, longitudinal cohorts, case control, cross-sectional studies, preclinical studies like animal and in vitro work, and opinions, and maybe even case studies. But what's really important to consider when even thinking about a hierarchy of evidence is that it may be useful if we're thinking of a causal question. In particular, what we're often interested in nutrition is the idea of a manipulable causation. What can we change to see an outcome? And that is often implied, but something that we don't often say. And sometimes, people will write an observational paper and say, well, because of residual confounding or the observational nature of this research, we can't conclude causation. That's great to try to hedge our findings and to make sure that we're communicating that uncertainty. But far too frequently what follows up is, and thus, from this observational study, we should change public policy. Or, we should work with physicians to roll this out into communities. Well, why would you want to change policy, or why would you want to get physicians to change their practice? Because you think there's an effect. You think it's cause and effect. But the other part that's really important to point out about it is there are some very interesting questions that people want that are just prediction. We want to know what people are more likely to have a disease, for instance. In those cases, this hierarchy of evidence might not be appropriate. You want a simple random sample of the population sometimes, or a stratified sample, or some way that you can probabilistically estimate who's going to have something. You don't get that in randomized trials most of the time. Most of the randomized trials are going to be convenience samples. So the first thing we have to think of for designs is what is the research question we have, and typically these are made for causal questions. Of course, determining where something falls on the hierarchy depends on the PICOS elements, and PICOS is an acronym meaning population, intervention, control, outcome, in either setting or study design. So if you had a study where you were looking at the effect of a diet on blood cholesterol in a randomized controlled trial, well, you've got a pretty good understanding of the intervention. Hopefully you've got a good idea of the control, and you've got a good measure of the outcome because you're measuring the blood cholesterol. But unfortunately, we don't really care about blood cholesterol in and of itself. We're interested in blood cholesterol for things like heart disease. So in that case, you might go to an observational study where, again, you're trying to estimate somebody's exposure in this case rather than an intervention, and that's going to be from self-report. You've got some estimate of the comparator, but maybe you have a really good estimate of the outcome, which is actual death from cardiovascular disease. Where do those fit here? You've got a stronger internally consistent design where you have a good estimate of the exposure and the comparator, but you have an outcome you care about less. And then over here, you've got the outcome you want, larger sample size, but your estimate of the intervention and control isn't as good. So it's not as simple as just stacking things up. If the studies were exactly the same, then yes, you might stack them this way. The other thing is that when we're talking about longitudinal cohorts or observational studies, we're frequently talking about something that has been coined as ordinary association tests. And that's described here as observational studies on samples of individuals in which the sole or primary means of controlling for potential confounding is inclusion of measures of some potential confounding factors as covariates in statistical models. So it's basically running a regression and just controlling for things. Those have substantial weaknesses, and we'll talk about some of those. But there are lots of other designs and analyses that can occur between a longitudinal cohort analyzed from an ordinary association test and randomized controlled trials. And again, the idea of this hierarchy is limited because there's lots of different designs. If, for instance, there is something that you could change about yourself, maybe you want to see if a particular diet helps you lose weight, you can change that. So maybe an N of 1 study on yourself is going to be better than the generalizability of a randomized trial. So I just wanted to start with this to talk about the complexity, to really rip apart this idea that we've got, observational studies and RCTs. There's a lot going on in the middle, and even which one is considered better takes a lot of thought and a lot of critical evaluation. So for stronger designs, again, here's a simplistic causal graph. So I mentioned confounders, and that term is thrown around a lot. But here what we're going to be talking about is an exposure, such as a diet or a nutrient, and then an outcome. I talked about blood cholesterol or cardiovascular disease, but any particular outcome you might be interested in. And then the idea of a confounder that correlates with X and Y or causes X and Y. So when we think about some of the causal modeling, at least in the simplistic framework, a trial breaks this leg here because you are assigning the exposure. So you know that at least part of your exposure is being assigned exogenously. That's why it's so powerful, or one of the reasons why trials can be so powerful. But I also mentioned alternative designs. So people have gone through and looked for potential natural experiments. You could think of things like natural disasters. You could think of things where nutritional exposures are introduced to different markets seemingly randomly, and the hope is that these natural experiments might break this causal leg as well, with the idea of really trying to dig in and to how do we know somebody got a different exposure without it being, for instance, for their own personal choice. And for an analysis, we'll talk about that that does this as well as Mendelian randomization, and we'll get to that as an example. But the flip side is a problem that we brought up. Again, this is starting to get a little dated. It feels just like yesterday. But my wife and I and David Allison worked on this question that we thought was going to be a lighthearted question, breakfast and obesity, to point out some of these challenges. And little did we know how passionate some people feel about breakfast. But here we just did a cumulative meta-analysis of association studies that were almost exclusively cross-sectional. There was a handful of longitudinal studies asking people whether they ate or skipped breakfast, sometimes measuring obesity, often asking about weight status. And the whole point of this slide is that even the first year of the meta-analysis that we put together, we were beyond the traditional p less than 0.05 for significance. After the second year of studies that we put in, it was 0.001. And then over the years of studies that we included, the p-value was 10 to the negative 42, which I believe is close to the number of protons in the universe, so randomly selecting one. And the idea is that at some point, we're probably not getting more information from another association test between breakfast and obesity. There may be some compelling questions to still answer, but the number of studies we've seen, even since we've stopped, where somebody asks, did these children eat breakfast and did they have obesity? It still continues, and we're not getting more information from those. I think we know from here, yes, they're associated. So it's what can we do? How can we take it to the next level? So we could consider really complicated designs or analyses, but there's really no reason why we can't do a randomized trial on breakfast and obesity. People will say that sometimes they're unethical or impossible, but eating and skipping breakfast versus obesity is something that is absolutely something we could do in randomized trials. So we did meta-analyze the randomized trials that had been done, but they were very few and far between for such a tractable question. And the sample sizes were pretty small. We've got from 10 to 109. The weeks were less than 1 up to 16. But what you see here is, despite that consistent association, each one of these meta-analyzed effect estimates was pretty squarely centered on 0. So we look at the observational evidence, there's an association. We look at randomized evidence, we're not seeing an effect. So asking people one more time what they eat and whether or not they have obesity is probably not going to move the needle. We need to figure out what's going on, and one more ordinary association test isn't going to help us get there. So, for stronger designs, I mentioned briefly natural quasi-experiments. We can also do group randomization. That has been done with breakfast in schools, for instance. There's also smart designs in the MOST framework, so we can get even creative with our randomized trials, N of 1 trials where it's appropriate. There's also the idea of a large simple trial where you just randomize a whole bunch of people, but you don't try to answer everything. The whole point is lots of people answer one question well, and even some family-based designs where you're using, for instance, twins and genetics. So there's lots of other things that we can do, and some people are doing these types of studies. But frequently what we see in most headlines are ordinary association tests, which have substantial weaknesses for causation. There's many designs between an ordinary association test and RCT, and anytime you hear somebody say that an RCT is impossible or impractical or unethical, it's always helpful to push back a little bit and say, well, is there something we could do? Is there some way we could intervene and really try to build stronger evidence, particularly if we're able to intervene? Because again, ultimately what we're hoping to do is change people's diets in a way that'll change their outcome. The ultimate goal is to intervene. So what about stronger measurement? So the status quo, of course, is self-report. Whether it's a food frequency questionnaire or a diary or other approaches, we ask people in different ways what they eat, and then we collectively, estimate intake from those. Often you'll hear a pseudo quantitative food frequency questionnaire, and of course, pseudo means fake. And so right there in the name, we're getting possibly ordinal relationships. But it's, this is a point I don't think I have to belabor, but I just wanted to point out that even people that use self-report a lot make statements like recall is notoriously unreliable as humans are notably bad at remembering detail. I don't want to mischaracterize their entire point of view. I include their names here not to criticize them, but just because these are big names that do use self-reported dietary intake. They do mention the potential value of it in this paper, but even the experts know that there are challenges with self-report. On the other hand, for things like energy balance measurement, we had put this out some years ago now, with the idea that we need to move beyond certain specific measurements that we know are so bad that it's actually misleading the science. And self-reported energy intake is one of those, where self-reported energy intake and energy expenditure from self-reported physical activity is so poor that they are wholly unacceptable for scientific research for energy intake and energy balance. And this isn't something that we come out with lightly. In fact, people had pushed us to say that about other nutrients and other self-report, and we didn't know. We really didn't have the evidence, but we did for energy intake because we have an objective measure. We have doubly labeled water, and we have other approaches. And after a half century of research, at least, it became very clear that self-reported energy intake wasn't getting us where we needed to for obesity research. So it's tough. And the question is, where does that leave us? And are there actual good uses for self-report? So one of the things we wanted to look at with that idea is to look at whether or not this idea of Goldberg cutoffs, which is removing allegedly implausible reporters, could actually correct the bias in these four estimates of nutrient intake. So we have energy intake, we have sodium intake, we have potassium intake, and we have protein intake. And so this is from the iData, the Interactive Diet and Activity Tracking in the American Association of Retired Persons data set. And you can see that there is a bias here. That's the red square is an indication of the population average estimate without correcting. So just using what people report versus an actual biomarker. But the black square here represents what the intake estimate would be if you removed implausible reporters. And you can see that removing implausible reporters put that square right back on that diagonal line. So when the biomarker is 100, the self-report is 100. So I had to eat my pride a little. I did not think this was going to work, but what we saw was getting rid of implausible reporters actually recovered the population average intake compared to biomarker intake. So that sounds like a contradiction from my last slide. But let me show you what we are really interested in. So what we're interested in isn't the average intakes because we're interested in manipulable causation, right? We want to know what is the association and ostensibly the effect of these four nutritional markers on health-related outcomes. So we have body weight, we have waist circumference, heart rate, systolic blood pressure, diastolic blood pressure, VO2 max. So what we did, there wasn't enough data, so we did have to simulate this a little bit. So that's certainly a limitation. But we've got the self-reported data. We have the self-reported data after throwing out people that according to the Goldberg rule were implausible. And then we have biomarker data. And what you see is the self-report, again, with body weight is exactly what we would expect. There is a major bias in the estimate of the association between self-reported energy intake and body weight. When we corrected with the self report after applying the Goldberg rule, it got a little better. So it's worse here, but compared to the biomarker, it was still pretty bad. So in many of these cases, and same thing with the mean square error and the coverage probability for these, and I enjoy talking about the ins and outs of the statistical aspects. If you want to know more, we've got the paper here, and I'm always happy to answer questions about that. We saw that with energy intake. Sodium intake, for some of these, it didn't seem like the Goldberg rule did much at all. And frankly, that's kind of what you would expect. The Goldberg is throwing out people who are implausible based on estimated energy intake. So what we ended up seeing is that the Goldberg rule sometimes improves self-report for the association between the intake and the outcome, but rarely to the level of the biomarker. And again, just to make this important distinction, one approach for the self-report is recovering an estimated intake of a population. That is a very different question than what is the relationship between that intake and an individual. So what it could be is that people who have a particular level of misreporting may also have a particular inclination to have or not to have the outcome. So if you're throwing people out, you're going to alter that association in ways that we don't know. We won't know because we don't know who we're throwing out. So it sounds at first like I'm kind of skewering this Goldberg rule. That's not the case, because I actually had a colleague after I presented these come up to me afterwards and say, that's not what the Goldberg approach was ever meant to do. In fact, the original paper, if I recall correctly, doesn't say throw people out and then run association tests. It was trying to get at that average population intake. So this is just an empirical indication that the Goldberg rule is not meant to recover those associations. So that ends up being a problem because many ordinary association tests you see out there will say, we threw out these people that consumed over 3,500 calories, or the Goldberg rule. So they're just throwing people out that they don't trust. But those are real people with real intakes that occur on a distribution. And to throw them out because you don't like how they reported their intake may have unfortunate consequences for our ability to conclude things from the evidence. So a few thoughts generally on stronger measurements. Again, this is just a snapshot of many, many different topics, but I put here self-report that is fit for purpose. So it's not that self-report is all terrible in all circumstances, but what are you trying to do with it? What does it mean if your self-report is wrong? Do you have a good validation of it? Have you actually demonstrated that the self-report is valuable or correct for a particular association you have? But unfortunately, frequently what we see in the literature is people will take the self-reports and run regressions on them, not do measurement error correction, not take these issues into consideration. So there's ways we can use the results more strongly. I didn't put a slide in here on this, but one of the fun ways that self-report ended up being illuminating was comparing the self-report in a weight loss study against an objective measurement of energy intake. And what you saw is that over time, the objective estimate of energy intake went up, and that tracked with weight, that people's weight started going up, but their self-report said that they were still eating less. And so the cynic would say, oh, well, they're just lying and things like that. And it's like, or maybe there's a psychological component in there that is indicating they really are applying the same amount of self-control. So it's the same cognitive load and they think they're doing as well, but they're actually not. And so that there's a dissonance between what they're reporting and what they're doing. That's fascinating. That is a fantastic use of self-report. But we just shouldn't believe the self-report is their actual energy intake, because the physiology is showing it doesn't match. So we can consider whether or not our adjustments are affecting average intakes versus associations. We need to keep building these methods, the biomarkers and technologies. There's some great food photography, a lot of great biomarker work, sensor technologies for swallowing, eating, chewing, Adam Hoover's wrist roll for bite counting, all kinds of these other approaches to estimate eating behaviors, ingestive behaviors, and the biomarkers. And then there are some really fascinating approaches people are taking to try to get some good measurement error correction. But all of these are things that could be applied, some of them to existing approaches to take those observational studies up one more level. Don't just throw people out. Don't assume the measurement is fine. What can we do to kind of ratchet up the quality of those studies? So moving on to stronger analyses, I mentioned briefly Mendelian randomization. And so again, we've got potentially these unmeasured confounders here. We've got our exposure, we've got our outcome, but then along comes genetic variants, so single nucleotide polymorphisms that we think affect the exposure. You know, a classic one is, well, a pair of them. One is lactase persistence. So if you are lactose intolerant, you're not going to consume as much that has lactose in it. And where is lactose? Well, that's in dairy. So now we've got a potential genetic effect on dairy intake. And so that is helping to break this leg here by indicating that that's effective here. There's also some genetic variants related to alcohol intake, for instance, and alcohol metabolism. So is there something about somebody's genes that is affecting whether or not they would have a particular dietary consumption? So the second assumption is that the genetic variant affects the outcome only through exposure X. And so if it's occurring somewhere else where this genetic variant also affects blood cholesterol through cholesterol metabolism and your outcomes, heart disease, well, now you don't have this nice, clean effect on the intake. And the third is that the genetic variant isn't associated with the confounders. So it's a powerful method if done correctly. Not to be a downer about it, but unfortunately it's become so easy to do that people just churn these out without really thinking about the science and digging in. So you do have to be careful when you see it, but at a minimum, you know, it's trying to get a stronger causal method than just simple regressions. But there are some studies where people still need to engage and to think. And so one example I saw was single nucleotide polymorphisms and different types of dairy intake. So just from a first principles thinking part, what is the SNP that would make you drink 1% versus 2% milk? Maybe there's something out there, but that the logic was never justified in the paper. Now, I think this paper also included dairy versus soy. That could make a little bit more sense. People that maybe are not having dairy might have more soy. Okay, now we're putting something together that's making a little bit of logical sense. But what about single nucleotide polymorphisms and exposure to air pollution? I've seen a few studies do this. What is the genetic variant that is going to cause your exposure to air pollution? And people could say, oh, well, maybe you have asthma, so you avoid places, you know, with high air pollution, which shows a real disconnect between, the idea of this model and social determinants of health. People are not able to just get up and move away from air pollution. So it doesn't quite fit the logic. So there's still thinking that needs to be involved, but it's at least, you know, something that's trying to move beyond just the simple regression. But there's also a lot of other decisions that can affect outcomes, and so analytical approaches that really kind of tease at some of our assumptions could be valuable. And here's an example of what we had worked on, particularly with Healthy Plant Diet Index. And this diet index included 12 food groups, and so we just decided to recapitulate it as they did it, without necessarily disagreeing with the fact that anything with an animal food in it was negatively loaded. So we just said, all right, they said anything with an animal product has a negative score, and then they divided all plant foods into either healthy or unhealthy. So we wanted to see what happens if we just built random scores. And so there were 12 groups, so that's 2 to the 12 different ways that you can combine them. So we came up with 4,096 healthy and unhealthy plant diet index scores. And what we see is that, as you would hopefully expect, it's centered on the null. So the null here for the hazard ratio is 1. because we're just randomly assigning them. The mean of all these should be 1. But you can have a little fun with it and tease it apart. So what you can see is that, when something is reverse coded, that means as it's lower, it's considered bad. And so you can see that with whole grains, what would you expect? Well, if it's loaded positively, then you would expect lower hazard ratios if you think whole grains are healthy. So you see that shift here. You're not really seeing it in men. So in fact, there's a slight shift this way for whole grains in men. What about potatoes, which was really the genesis of this project, because the Healthy Plant Diet Index decided all potatoes were uniquely evil. Everything else was a group of foods, but potatoes had its own negative category. We see no real difference, maybe a slight uptick for men. But what about sweets and desserts? There was this wonderful paper, I think a lay article about nutrition science's most insidious secret or something like that, which is that ice cream and sweets and desserts keep being shown as being beneficial in a whole bunch of studies. And so what do we see here? We see a shift where sweets and desserts for women are starting to shift positive. I have not yet told this to a woman who is upset at those results, but every man I tend to tell it to ignores the fact that it seems potentially detrimental here. So you can see that when you start shifting these things around in here, these arbitrary classifications of food as healthy or unhealthy, you might get strange results. And in fact, in this case, we found a healthy or unhealthy index for each of these food groups. Now, the limitation we still have is we don't exactly know what to do with these. This is a new way to look at this, and we don't really have a good idea of what to do for an inference. Is this something we should be concerned about? Does this look like random error? And so we've got a lot of work to do for the limitations of our own approaches. But it's still interesting that if you move foods around, in these categories, you could create an index for any food you want, at least amongst these, where you could find one that's, beneficial or detrimental for that food. I want to be clear. That comment has been misinterpreted sometimes for me to suggest people are p-hacking or trying to design these things in a nefarious way. I don't think that. I don't think people are trying to construct these in a way to mislead people. So I want to be clear about that. But it's just that if and I did have a colleague who said, well, she didn't believe that potatoes were bad, so she moved them in her index. That's not a criticism of her either. It's when we've got these arbitrary decisions on making an index, those things can happen. So what do we do about it? That's what we really need to figure out. We need to spend some resources on that. There's also the idea of specification curve, multiverse, arbitrary model decisions. And so we worked on a project with this looking at beef intake and coronary heart disease. Because we were just curious, what happens if we create one of these ordinary association tests, but define those covariates differently in the model? Because different data sets will have different covariates to try. Different data sets will end up having different configurations, and different epidemiologists will decide that the model should be fit differently. These are all, again, potentially legitimate decisions that people could make. I'm sure somebody out there is nefarious about it, but I don't think that's the majority. I think most people are building models that they think are reasonable. So what we did is we did 2 configurations for beef. So we used quintiles, which is unfortunately used very frequently in nutrition epidemiology, and then continuous intake. There is also exclusion configuration. So we talk about the Goldberg rules. A lot of studies will say, oh, if somebody's above this many 1,000 kcals, then they're estimated to be an overconsumer or an overreporter. And so that could be split by men and women or just a general threshold. So there were 7 different ways we saw people exclude individuals. And then we found in the papers we looked at 33 covariates with 117 different configurations. Together, that resulted in the potential for 4.16 quadrillion model combinations looking at the generic question of beef intake and coronary heart disease. And I'm using the word quadrillion actually as the number, so 4,160 trillion, I'm not just saying gazillion. It really was that many potential. So we wanted to run them all, but my colleague estimated that it would take about to the heat death of the universe for our supercomputer to run them all. So we only did a million. So what this essentially does is simulates a million epidemiological papers that could have all been defined different ways. And so you can see these different distributions, and I won't belabor them here, but you can see that we get different z-scores, hazard ratios across quite a range of estimates across these million models. And notably, very few of them ended up being statistically significant by the traditional thresholds. So what's another way to look at this? So this is the specification curve, and all this is for the x-axis is the rank order of the hazard ratio. So we didn't put error bars necessarily in here, but you can see we get hazard ratios well below 1 to hazard ratios above 1 across this distribution here. But what's interesting is how that distribution changes depending on if we used quintiles or continuous. So most of the continuous estimates, which is frankly more informative to me, but people disagree with me about that, you're seeing that it hovers around, more closely to the null, although there is quite the distribution. With quintiles, you see many more high hazard ratios out here when you're expressing beef intake as quintiles. Again, the statistically significant ones are going to be out here in the tails. That raises a lot of questions, which of these models is right, if any? And so it's important to consider what the variables are actually doing in the model. So here's simplistic causal diagrams. We talked about confounding. Here I used Z instead of U, but there's also mediation. So does the exposure cause something in the middle that causes the outcome? Here the exposure might cause another variable and the outcome causes another variable. And then you've got covariates. So we looked at some of those as well. These are the distributions. And here, again, like if you put this under that previous figure I showed, you can see that there is a shift in the distribution of the hazard ratios depending on just whether or not a variable was included. It doesn't even tell you how it was included, but these can each shift things. So imagine that you had an exposure and an outcome that both changed the probability of income. If you threw that in the model, you would actually be getting the wrong answer. But very rarely does anybody define this structure with the variables they put in. Often what we do in these models is just put them in as general terms. So there's a number of people who are calling to put more causal diagrams in rather than just throwing terms into the model to make us stop and think. What do we think that relationship is amongst these variables instead of just saying they're confounders and covariates? And you might say 4.16 quadrillion, surely we could use AI and machine learning. AI and machine learning can't save us, at least yet. There have been lots of advances, but this paper led by Diana Thomas, we outlined some issues that are still found in AI and machine learning in nutrition to date. Again, measurement error, selection bias, sample size calculation, missing data, data imbalance, explainable AI, and data literacy are all problems that really perpetuate from any of the models we've talked about to AI and machine learning. So those same problems are there. We still need to think and work through how we're going to answer those. So to wrap up on the stronger analyses, to beat the drum again, it's the ordinary association tests for the small differences that we're looking a lot of the times. They're not fit for purpose for most of the questions we want to answer. There's also no reason that we have to just limit to one analytical approach, especially when there's lots of arbitrary or even purposeful model decisions to try. There's lots of creative approaches being developed. I showed a couple of them today. They've got limitations, and we're still learning a lot about how to interpret them. And then even an advanced analytical approach still requires that scientific thought. So to wrap up with stronger execution and reporting, basically, I think this sums up a lot of what we're up against in nutrition. That is, high quality evidence may be difficult to attain in nutrition and chronic disease research. It's uncomfortable, and a lot of people are afraid to say it, or if they do say it, they will use it to denigrate the field and just say, why trust anything? And this was summed up in part in a commentary talking about the grade approach for evaluating evidence, which is formally identifying effects which are regarded as important and based on high quality evidence using the grade system may be unattainable in the context of nutritional determinants of chronic disease. So, starting with the fact that this is a very difficult field, I think will really elevate the field, frankly. I think the fact that it's so easy to grab a data set and run a regression has made it seem like the field of nutrition is easy to get into. But what we've just laid out today is how hard it really is to answer the questions that we want to answer. And so what unfortunately some people have done is tried to come up with alternative systems to evaluate nutrition evidence rather than just saying the field is difficult and we may not be able to reach the highest tier of evidence that we want. And so the grade group responded to one of these systems because that system indicated that a blinded randomized trial was a limitation of the grade approach. Well, that's not the case. It's a limitation of our field, that we can't necessarily blind people, and expectancy will always be there as a potential explanation, even in randomized trials. That's just a limitation of our evidence base, and we need to get beyond it. For this other approach, they indicated that randomization would not be critical to balance known and unknown prognostic factors in nutritional studies, but they are. That's an important point of randomization. And they also had proposed in this other approach that funding bias should be assessed as a separate item. But we know that that's not a legitimate way to evaluate bias in evidence. Another alternative system created kind of this pathways of whether or not a question is addressable with RCT. So they said a sample size must be less than 10,000 and measurable within less than 5 years. Well, why? If the question is important enough and we've got a good enough scientific basis for it, why wouldn't we throw this? This is less than many vaccine trials. This is less than a lot of trials. If it's important enough and well-founded enough, then it potentially is answerable by an RCT. And I was just on a call with John Sievenpiper with the I think it's the CHEAP trial. They're looking at outcomes up to 7 years. So it's doable. But even if an RCT is not possible, it doesn't mean the weaker forms of evidence are suddenly stronger. It just means it's a limitation of our field, and we just need to get a little bit more comfortable working within that uncertainty. The causal inference, again, is not different for nutrition, but reporting can be. So one of the things we can do is describe our studies better in ways that help people understand where it fits in the complexities of causal inference. So here's just a few examples from the Strobnut statement for the strengthening the reporting of observational studies in epidemiology, nutrition extension. It just talks about some things that people want or need to know to make sense of nutrition epidemiology. So the idea of causal factors is the same, but how we get there might be a little bit different in nutrition. So finally, it wouldn't be a talk about communication or a section on communication without talking headline versus study. This is one of the highlights of my week, is to put the headline versus study together for the obesity and energetics offerings. And this was just in the same week, a lay article says not having breakfast could make you unhappy. The study says, but the design of the study was a cross-sectional association between how often do you typically have breakfast and a 10-point subjective life satisfaction assessment. I think that lay article title is a little extreme, but if you even look at the title of the article, is the frequency of breakfast consumption associated with life satisfaction in children and adolescents. 154,000 participants from 42 countries. Still cross-sectional correlation. Conversely, this lay article was titled, Our Research Suggests Eating an Unhealthy Breakfast Could Have a Similar Effect on Your Child's School Day as Having Nothing at All. But wait, I thought not having breakfast could make you unhappy. So we're getting these conflicting headlines same week, This was again a cross-sectional analysis of a single morning's breakfast consumption and quality with a motivational questionnaire and a 12-question science test. So we need to do better reporting our own studies. We need to adhere to reporting guidelines. We need to lay out exactly where we fit on the continuum of causal inference and strength of evidence, which sometimes we're not going to be able to get that large randomized trial confidence that we really want. And we need to communicate it clearly. And we need to encourage media to report it with the similar caveats, because it's very hard to blame journalists and the lay media when we ourselves are in the field spinning our conclusions a bit beyond what they can say. So what about going forward? So as I mentioned at the beginning, I don't want this to be all downer type of material. I hope I showed paths forward. So I hope I showed where there's some limitations, why it's concerning to me and others, and paths we can do to move things forward. But if there's any trainees, early career scientists on the line in particular, sometimes this gets to be a little bit concerning, right? So all of a sudden, maybe you have a skill set of running some of these ordinary association tests, and here's this guy saying, oh, we need to move beyond that. So I think an iterative approach, there's a lot of people out there that push for everybody to go with best practices. And I joke that a lot of my career has been spent helping people avoid worst practices. We don't know what the best practice is. But what if we made at least one improvement that we talked about today in each study we conducted? Stronger design, measurement, analysis, execution, and reporting, and just try to iteratively improve the quality of the field and say, I think what you have in front of you with that observational data set, maybe you could use a creative approach, propensity score matching, maybe do one of these multiverse approaches and say, I'm going to push a little bit further than I was originally comfortable doing. So from this quotation from Stuart Ritchie, rather like psychology, nutritional epidemiology is hard, all the more reason that scientists need to take more seriously the task of sensibly communicating their findings to the public. We need to try to do stronger research, but we need to communicate it as such. But also I like this quotation of epistemologically, there's no reason nutritional science should settle for lower standards. Our field is difficult. We need to acknowledge that. And we need to try to use some approaches that can maybe strengthen our field and strengthen our communication, especially as we're looking for more and more nuanced effects and associations. So thank you for listening to my remarks. I hope there's some good questions. Always feel free to reach out and continue the conversation. And at this point, I think we're open for question and answer.
Sounds great. All right, we have a bunch of questions in the chat, so let's go ahead and get into it. The first question is, do you think there's an issue when there's a lot of data in nutrition that's non-normal, so either skewed left or right, but the assumption is that data is normal? Is it just, it's easier to analyze the means rather than the medians, which could skew the results? So what are your thoughts on non-normal versus assumptions on normalized data?
So I'll give an academic response of it depends. So there really are some models that are pretty resilient to issues with normality or skewness. So I think it very much depends on what the model is that you're looking at. I think the idea of quintiles versus mean differences is certainly an example there. So if you're fitting, like I showed you with the beef and coronary heart disease, if you're fitting a continuous model, that's assuming something about that relationship, whereas the quintiles are taking the lowest and the upper chunks. So it's attractive in that way because you basically ignore some of the issues with the distribution. Yet we know that, what does intake look like for a lot of things? It goes up and then it skews way out to the side. So you've got somebody who's, eating, a pound of steak, every meal. And then you've got somebody who is a staunch vegan, and you're pooling those into other groups. So I don't think, it's as simple as normality versus not. I think it's really asking the nuance of the question. Also, often with the models, It's not the normality of the actual variable, but the normality around the error of the model. And so looking at the residuals helps. But I think another question that was kind of hinted at there is, should we even be looking at means and averages? And there's some people who have made compelling arguments that no. I think some of the Nutrition for Precision Health is looking at that. But if you're creating dietary guidelines for Americans, which I believe the meeting is going on right now, so if you're on the call, thank you for hanging out with us instead of seeing that. But they need to make recommendations for people in general. And often that's going to be, what do we expect to happen to people on average as a place to start? So I hope that was not too circuitous of an answer to that question.
No, that was great. There's another question going back to your fit for purpose point. In some ways, aren't subjective measures even more important than objective measures when most of us eat by intuition or feel rather than counting by macros or energy?
So whether it's there, I get to say it depends again, but I think you laid out in that question it depends. So what are we talking about? Are we talking about a world in which, let's say it's a nutrient, and we can put that into or take it out of foods, whether it's something that you can do in your kitchen or something that is in, more of the mass-produced foods? Well, then you don't have any intuition about the amount of iodine in your salt. You don't have any intuition into the fortified nutrients in your bread. On the other hand, if you're looking at ingestive behaviors, then absolutely. But then we need to change our communication, because what you don't see in a headline or even the title of a paper, we'll use that beef example. It's not, it's usually the effect of beef on heart disease. It's not, the association between people who report eating beef and heart disease. So if what we're talking about is people's perspectives and intuitions and how much they think they've eaten, then we need to make sure we're communicating accordingly. And at that point, we're not trying to talk about a specific food or nutrient. We are talking about what people think they're doing. But it's an excellent point that we need to make sure we're matching our studies and our communication with what outcome we're particularly interested in.
Okay, interesting. There's a question here about, you mentioned the next steps. How can we move on from this? Are there any books or articles you could recommend to further explore these issues?
There's a lot. I've been fortunate to be involved in some. I'm not sure if there's an opportunity to share additional resources at the end of this, but
Yep.
not to be a shameless self-promoter, but it's just the one that I'm most familiar with is our courses on causal inference and mathematical sciences and obesity. That's where we like to focus on these, and usually the speakers that we have, sometimes we have as many speakers as participants, and then the speakers become participants. But we do have those archived, and usually they will provide some references along with it. Depending on what it is you're wanting to look at more on the statistical end, there's certainly things like Statistical Horizons that do a lot of courses. I'd say for the American Journal of Clinical Nutrition, the Best But Oft Forgotten Practices series covers things like cluster randomized trials, power analysis, I think propensity scores, mediation, and so that's a good series. And then the JAMA's User Guide to the Medical Literature has a lot of the concepts. I don't know that as much how-to, but they do have a number of things for considering evidence-based medicine. So those are a few things that come to mind off the top of my head.
Yeah, absolutely. Well, it looks like we are almost about out of time. We have about a minute left in the webinar. I want to thank you, Andrew, for your presentation today. I found it personally informative. Also good that I can eat ice cream, it sounds like. So that's
don't quote me on that one.
asterisk there. So I really appreciate your presentation today. I would be remiss if I didn't remind the audience that IAFNS is hosting our Science Innovation Showcase this December. We're currently accepting abstracts for that, so please go check out our website for more information on that. And again, thank you, Andrew, today. It was a great presentation.
Thank you.
Thank you, everyone.